I want to spend a little bit of time talking to you about fatigue. And we've made a few videos so far about fatigue in terms of the depletion of fuels and the buildup of metabolic byproducts. However, just before coming back from lockdown, we had an online Zoom lesson where in breakout groups you were divided up into different sections of the aerobic system's reasons for fatiguing an athlete during exercise. You came up with a summary sheet. That summary sheet has been uploaded onto Compass for your perusal with dot point forms. But I thought as we go towards a SAC in a few weeks' time and the exam at the end of the year, creating this as a reference point for you to be able to go back and watch might be handy. I'm at the textbook section of page 170 now, and we're talking about fatigue in the aerobic system. And as was outlined in that Zoom conference, we're talking about here being in the aerobic system and being in the aerobic system for longer periods of time. So things like 20 to 30 minutes, and knowing that we're not at maximum heart rate, we're less than 85% of the maximum heart rate. Because as you should know by now, if you are training at 90-95% of the maximum heart rate, the body will be predominantly relying on the anaerobic energy systems, ATP-PC and anaerobic glycolysis. So if we want the body to be going through the aerobic energy system as the dominant energy system while the other two are working in the background, we need to lower that heart rate and intensity down a little bit. That's an energy system that can last for quite a while, but don't forget there are 4 things that happen when the pyruvic acid bonds with oxygen. We've got additional energy for ATP, carbon dioxide, which we can breathe out, H2O, which is water, which we can sweat out to cool us down, which you'll hear about in a moment, but also heat. And heat can be one of the major causes that the aerobic system makes our body fatigue. Otherwise, we could just continue to run forever. So, a few dot points here to actually think about before we move on. Elevated core temperatures. So the body's temperature, what is it to start with and what do we not want it to get to? Increased rate of dehydration. Rate meaning how quickly this happens. So every day we have to continue to drink water so that we stay hydrated. So dehydration is actually occurring every day because the waters that we consume are being used up by the human body. It's just that when we start to exercise and the heat builds up, the rate in which dehydration occurs is actually happening quicker. There's a redistribution of blood flow to assist with cooling. We know that the blood stops flowing because of vasoconstriction towards the working muscles, therefore less oxygen is actually being received at those muscles. And vasodilation, more blood starts flowing towards the skin so that the pores can open up and we can sweat to cool ourselves down with that elevated body temperature. We end up with a decreased plasma level, which I'll talk about momentarily. We end up with elevated blood pressure because the blood is having to be forced out a little harder because once again, as I said, the muscle itself is not receiving enough oxygen now, is sending messages back to the brain saying, I need a bit more oxygen, so the heart starts working a little bit harder and putting pressure on the walls of those arteries to get more blood down to that working muscle to get back into that aerobic system. We get an electrolyte imbalance. I need to spend some time talking about that. And the central nervous system talks about decreased firing. And I'll talk about the governor system as well. So, the human body likes to be between about 36.5 and 37.5 degrees Celsius. Anything below or above that, and the body starts to actually try and regulate itself a little bit better. So if it starts to get to, 37.7, the body will do a lot of very severe measures to cool us down. And if the body ends up going down below 36.5, it will do things like shiver and we will get goosebumps and try and rub those bumps out so that we create friction and heat the body up. When the heat production exceeds the heat loss, the body has mechanisms to help us lose heat, but when the production of heat, so the aerobic system comes into play, exceeds that, it's like talking about the lactate inflection point. When we build up too much lactic acid and we can't get rid of it, now when we build up too much heat and we can't get rid of it, same mechanism, what ends up happening is hyperthermia may result. ER, not O. Hypothermia is when you are too cold. Hyperthermia is when you are getting too hot. So, as we start to produce heat, the body goes through thermoregulation. And when the body goes through thermoregulation, it starts sweating more profusely to try and cool the body down. The other thing that the body does is it tries to work out this skin's evaporative cooling by trying to actually allow some of the heat within the body to be lost by evaporating off of the body. So there's two different things that are happening here. One, when you look at somebody who runs and they are running, you will see two things happening. Number one, you'll almost see steam or heat coming off them. That's the evaporation. The heat off the skin is actually dissipating off into gas. And the other form that it comes off in is liquid, which is when you can see the beads of sweat pouring out of people because the pores have opened up and that comes out. When that happens, if you lose 1 to 2% of your body weight, so the easiest way you can calculate that is somebody who's 100 kilograms and goes for a run, and when they finish their run, they go back on the scales and they are 99 kilograms. They've lost 1 kilogram, which is 1% of their body weight through fluid. You guys know that I like to go for runs. I went for a run, 2 hours. I've talked to you about that run most recently. Prior to the run, when I stepped on the scales, which is something that a lot of athletes do, I'm not calling myself an athlete, I was 78 kilograms. When I finished my run, I was 76 kilograms. I had lost 2 kilograms of body mass. Hadn't been to the bathroom. It was all through sweat. And those 2 kilograms of body mass added up to about 2.5% of my body weight was lost throughout that run and needed to be replenished as well. So what ends up happening here, you can see that as you increase more and more of that sweat, significant changes happen within the body. And we've all seen famous pictures of runners collapsing at the finish line. Quite often they've lost way too much of their body mass through sweat. The cramping and the muscle spasms starts to occur here. So somebody who is continually replenishing water won't suffer this as much. However, it can happen quite quickly, and as you can see in that 5%, the 20 to 30% decrease, which is a huge amount in strength and power, ends up happening. So each muscle contraction is less. This part of the paragraph, I don't think we need to spend too much time on because it's talking about the vasoconstriction and the vasodilation, which I mentioned in the introduction, and about the body's mechanism to sweat to cool us down. And I think everyone in the class is quite comfortable with that at this current point. One thing that I will flip over and show you though is where is that water from sweat coming from? And hopefully you remember this from both year 10 and 11 PE type subjects, that the blood is made up of 3 things. Red blood cells, they carry the oxygen. White blood cells and plasma and platelets. The white blood cells fight off disease and the platelets help us when we scab over a cut so that we don't bleed for too long a period of time. And this big bulky section, which is 55% of the blood, which is plasma. Now that plasma is made up of just 90% water, so the majority of the blood is actually just made up of a water and fluid-like substance, and that is where the sweat is coming from to cool us down. Okay, on to the next thing that we needed to talk about here, and is also on your reference sheet on Compass, the central governor mechanism. This is actually quite difficult to remember, central governor mechanism, but it's very, very simple concept. Essentially, what it's saying is the brain is the central governor of your body, which makes sense. And essentially, the governor is the person who makes the decisions. So, the central governor is referring to the fact that when the muscles start to fatigue, that means they're becoming too tired, they're heating up too much, whatever is going on inside the body, whether it be acidosis, lactic acid, etc., that muscle is sending messages back to the brain saying, you need to slow down. I can't continue to produce ATP and energy for muscle contractions this quickly because acid is building up, I'm losing fuel, I'm heating up too much. When all of those things are happening, the central governor, which is the brain, starts to actually send less messages or weaker messages or something along those lines. And the next part of the textbook talks to you about what that is. Basically, it is saying this. There's a couple of things that we need to remember about it. I'm going to flip over to a diagram for you. This here is a nerve. That nerve has come from the brain down the spinal cord, which is inside the bones of the spinal column and branched out towards the muscle. These over here are the capillaries. They've come from arteries and arterioles. They're the ones that are carrying the blood. So oxygen can go out, carbon dioxide can go in, etc. in that diffusion. And this big bulky thing here, this is the muscle fiber. But if we go back to the nerve that I spoke about first, what you'll notice if you have a look at the zoomed in image over here, the nerve does not actually touch the muscle. The nerve has a gap, and in year 11 PE, we spoke about that being a neuromuscular junction. Now, with the neuromuscular junction and that gap, essentially in this section of the textbook, what they're trying to talk about is what's happening at that gap. There are a number of different elements that help the messages jump from that nerve into the muscle to allow that muscle to contract because it's received its message, to release ATP, for the actin and the myosin to be able to cross bridge. When this is actually becoming impaired and that gap doesn't have the elements that allow the message to make its jump, maybe the brain is still sending the messages, but the muscle is not receiving them. These are all theories. These are unknowns, but they're things that you need to understand, that scientists are taking tests on and trying to work out what is going on inside the body. And at the moment, it's the most commonly proved theory. So what we need to focus on is, as we sweat, we lose electrolytes, and electrolytes are the things inside the body that help reactions occur. So, sodium and chloride. Sodium is one of the principal positive ions. We've spoken about hydrogen ions and them being an acid, and they bring that pH down because they are the minus. What we end up knowing here is that sodium is a positive, so when we have sodium, it can help with that buffering process. So if we're sweating and we're losing sodium, which sometimes we can taste a bit of a salty taste in our sweat, then that sodium is not helping whatsoever with lactic acid buildup. It's not helping buffer it out. The next one here is potassium, and potassium really helps the body a lot when it comes to glycogen and glucose. When the potassium is around and inside the body, it helps transport glucose to the muscle cells. So don't forget, if the liver is able to create more glycogen from the lactate that was being built up, if we don't have enough potassium, we can't actually transfer that back to the muscle to be able to use it, so we're going to fatigue. The next one down is calcium. Now don't forget that when we talk about calcium, we're talking about that actin and myosin trying to cross bridge onto each other, and if calcium is not present, which was part of one of my previous videos, then this bond can't occur, so a muscle can't actually contract. So calcium needs to be present, and also magnesium, because magnesium's major role is to actually help with the relaxation of muscles. So remember the whole idea that if I want to flex my elbow, the bicep works this way and the tricep works this way. While the tricep's working, I need the bicep to be able to relax. So it contracts one way and then relaxes the other way. And if there's no magnesium present because it's been all sweat out, because it's part of what's inside that blood, then we can't relax that muscle and we're going to suffer from cramping, which is why a lot of people who do suffer from cramps will take magnesium tablets. The final part of this book before we move on to recovery is DOMS, Delayed Onset Muscle Soreness. This is pretty simple and straightforward, guys, but it is quite often misconstrued with lactic acid. So, delayed onset muscle soreness. When you exercise, and it's an exercise that you haven't done in quite a while, you're using muscles at different strains that you're not used to in your body, those muscles will suffer little tears. Or if you go and stack a heap of weight onto an exercise that you're used to 20 kilos and you're trying a 30 kilo rep, what ends up happening is the muscle is under stress that it's not used to. Those little microscopic tears that happen inside the muscle can be a good thing, because when we consume protein, they can help with muscle growth, muscular hypertrophy. But the problem is that if the body is not warmed up properly and these tears that are meant to happen end up opening a little too wide, then we end up with a lot of soreness 24 to 48 hours, 1 to 2 days later. Hopefully you guys now have a really good understanding of the fatiguing mechanisms and what can happen during prolonged aerobic exercise, and a lot of it is about the body heating up and needing to cool down, and what is lost in that cool down of the body sweating process, and how each of those elements being lost can affect brain functioning, muscle functioning, and fatigue. We'll come back to you soon with the next video, which is all about recovery from fatigue.